Hey there, good morning, good afternoon, or good evening, depending on where you are in the world. I'm Chris Down, I'm a kernel engineer at Facebook. I work on memory management, mostly in the area of control groups or Cgroups, which are one of the building blocks for modern Linux containers. I'm also a maintainer of the systemd project, small project which some of you may have heard of and or wrote an angry post about. In general, like my job is thinking about how can we help make Linux operate more efficiently and more scalably. It's quite important because at Facebook, you know, now we have 1 million plus machines. We can't just buy more RAM, we can't just throw hardware at all of our problems. We need to extract the absolute maximum out of each machine safely. So that's one of the things which I'm going to be talking about today. I know that nobody really gives a single toss about that though. What they really care about is that I was Arch Linux user since 2008, so I remember the bad old days of init scripts and all kinds of stuff, so yeah, nobody can bullshit me telling me those days were better. Especially as someone who works on upstream software, who works on quite core software, you know, I find Arch Linux incredibly useful. Having the latest core software available, having a great build system, all of that makes Arch really, for me, the perfect distribution for anyone who works on kernel, for anyone who works on systemd, for anyone who works on like upstream software. It's a great distribution if you are a developer and you work on those kind of things. So keeping recent, keeping rolling makes creation of testing of new features and fixes really, really straightforward. So I definitely give like a big thumbs up for Arch Linux, and that's one of the reasons I've been using it for so long, so thank you very much to everyone who's been involved in it. So memory management in general is the kind of topic which I want to talk to you about today. I want to help give you more of the tools and information which you need to manage memory at scale. There are many, many misconceptions, even among senior members of our community, about the primitives which we provide as the kernel and what they are good and what they are not good for. And memory management in general is a very inexact science, where basically everything is a trade-off between performance or accuracy. And it's not a mathematically correct science. You've really got to trade off. So I want to give you a better feeling about what trade-offs and what decisions might be applicable to you and your workloads, and hopefully you'll come out of this talk with some ideas that you might want to take away and apply as part of your memory management strategy and help make it more efficient or more reliable for your specific case. First, before we even go into that, let's cast our minds back a few years to 2017, the years before the big Rona hit us and left me stranded trying to record this in my own house. With the kitchen behind me. So I went to a number of conferences that year talking about Cgroup v2, and Cgroup v2 is our big bet as an industry for resource control and management in the Linux kernel. Cgroups are essentially a kernel mechanism which we're building to balance and limit and throttle things like memory, CPU, and I/O and that kind of stuff. Things which you share across a system and across applications. We have pretty good problems at Facebook, you know, our user base is increasing, our product range is diversifying, but with that growth comes scaling problems of a class which we've never really had to deal with before. And in the next few years, we're really going to feel this crunch for capacity, and we simply can't effectively solve this problem by throwing more and more hardware at the problem, not only because of expense, but because of availability. It's really starting to become a problem. And, you know, we have hundreds of thousands of machines. We just cannot afford to waste capacity. A small loss on every machine translates to a huge absolute loss across the fleet. So we need to use resources more efficiently, and Cgroups are one of the things which fundamentally allow us to do that. This is also really important as many huge site outages and incidents are caused by resource control issues. Not being able to readily control things like CPU, memory, I/O, it can really either cause or make worse existing issues, and we've seen this not only at Facebook but at a lot of our competitors like Google, Amazon, LinkedIn, all of those kind of companies. You know, we are having a lot of problems as an industry dealing with these resource control problems. So we need to start an initiative industry-wide to solve this problem, and that's a large reason why Cgroups by their nature exist. 2 years ago it was a totally different story though. We had really only one user of Cgroups, which was us. Even Google, which is now a fairly large user, hadn't really started using them at that point, and it took a lot of work and overcoming obstacles to reach the point where we are confident saying, you know, these are now ready for use in production generically. In general, in the old days, what happened was we had a whole bunch of cool and new primitives which we'd invented, which we were very excited to use and seemed correct. But when we actually went to go and use them, it ended up being something kind of like this instead. The primitives aren't really wrong. The problem is just that they are kind of on the right track, but we need to know in which cases we should make the primitives or the operating system a little bit more square, and the primitives maybe a little bit more round to achieve what we want. And knowing which of these makes sense in each situation requires a huge amount of testing and experimentation. Another problem in general is that limiting one resource artificially can, if you're not careful, just result in transferring all of its contention onto another resource. For example, if you limit memory too tightly for an application, then it likely will just become a huge amount of disk I/O, which is obviously not desirable. This is because we will start doing things like evicting the page cache, and might also start to swap pages which are harder or more in use than we would ideally like to swap. And as such, we need an underlying system which mitigates these issues, and we simply didn't have that back in 2017. This is also why you'll see me talking a number of times in the talk about I/O. You might wonder, why is he talking about I/O when we're overall kind of talking about memory? The reason is because without talking about I/O, we can only really have an academic discussion of limiting memory. So to be practically useful, you always have to have controls on I/O when talking about controlling memory, for the reason we mentioned just before about like evicting page cache, swapping out, that kind of stuff. Another problem is that while we have had Cgroup 2 technically working for a while, the past few years the major focus has been on issues which it has brought up elsewhere. Because Cgroup 2 limits resources in a way that was never really done before in the kernel, it has exposed a lot of these issues, these long-standing issues. They're not new issues, but we've never really had fine-grained prioritization, so they've never clearly been exposed in such a way before. And there's not enough time in these 45 minutes to really go over every single issue which we found, but I did go into them quite in detail at my talk in SRECon last year. If you Google for me at SRECon 2019, you'll probably find a lot more detail about the problems we had with ext4, with journaling, with memory mapping semaphores in the kernel, and so on and so forth. In general, like, the point is, we found and fixed a humongous number of issues across the kernel, from memory management to I/O to file systems all over the place, and a huge amount of our time has really been spent invested in improving resource control in these subsystems to not break down under scrutiny. So let's kick off the main part of the talk by discussing some of the fundamentals of Linux memory management. And this is really important to go over at this point of the talk, because if we don't agree about these, then the rest of the talk you're just going to spend like shaking your head. So we should at least agree what we're trying to achieve in the first place. And one thing that's really critical in understanding that is understanding in Linux has different concepts of different types of memory. From the CPU's perspective, they're really kind of all the same. It has some kind of concept of different permissions, but it doesn't know anything really about the semantic intent of the pages. For example, in Linux, anonymous memory is, as the name would imply, not backed by any backing store. Memory explicitly allocated by malloc and so on and so forth during a program lifetime typically is anonymous because it doesn't have anywhere else to go. Most people also know about caches and buffers, which are kind of two sides of the same coin. Nowadays, they're both part of the unified page cache in Linux, so I'll probably just refer to them kind of interchangeably as file pages or unified page cache or something like that. One of the problems is, like, if you ask most Linux users or most Linux admins, or even most senior Linux administrators, they will say, file caches and buffers, they're reclaimable. They can easily be trivially freed when things go awry. And they're not entirely wrong in that, but the problem is that people misunderstand what reclaimable means. Reclaimable doesn't mean like you can reclaim it. It means you might be able to reclaim it if you ask at the right time and we happen to be feeling particularly nice at that particular moment. So, for example, if some application is absolutely hammering on some file on the disk, right, it's very unlikely that we would evict it from the file cache, because we would just destroy the application performance. So while these can, under some circumstances, be freed trivially, it doesn't always have to be the case. And this can cause some confusion when people ask, why did my application run out of memory when I still had this free memory? And we'll come back to some more of these unexpected foibles in a little bit. The fact that these caches might not be evictable at a particular point in time is another example of why the resident set size, or RSS, a metric that we'd love to measure, is really kind of bullshit. RSS often unduly skews a lot of attention towards a few singular types of memory, anonymous memory and mapped file memory. And we forget though that many workloads simply cannot operate in any performant way without extensive file and buffer caches or other system-wide shared memory. So measuring RSS is kind of a losing game. And the reason that we measure it is not because it's a good measurement. The reason is because it's really, really fucking easy to measure, which is a nonsensical reason, right? It doesn't make any sense. Like, I don't understand how we've got to this point. So when somebody asks how much memory your application uses or your service uses, the only reasonable answer, unless you've compressed it beyond belief and found out the answer for yourself, like using some kind of workload compression, is that you have absolutely no clue like how much it actually uses, right? In one case inside Facebook, just as an example, a team that had for years believed their memory footprint was in the order of like 100 to 150 megabytes, found out that it was more like 2 to 3 gigabytes of critical memory working set size, just because of file caches and buffers and so on and so forth. So you really can't just exclude them from your memory calculations as if they don't exist, because it's not a reasonable way to operate your service or application. This is one reason why in modern resource control and in Cgroup 2, we limit all types of memory together instead of just trying to limit anonymous memory or one type of memory or so on and so forth. The problem there is if you limit just anonymous memory, or you do what Cgroup v1 did and limit every type of single memory separately, you're trivially going to allow the application to still cause problems on the system by thrashing the file cache or by using some type of pages which you're not accounting for. So it doesn't really work very well in the long term. This whole discussion also brings us somewhat neatly onto swap. Swap in general is a very widely misunderstood concept, highly controversial topic. A lot of people think that swap is mostly irrelevant nowadays with tens of gigabytes of memory. It's a little bit strange though, because for the things that swap is good at, you really cannot get them any other way. And for the things which it's bad at, it's usually entirely possible to mitigate them. So usually these discussions kind of hinge on these very large misunderstandings about swap is actually intended for, especially being that it has almost absolutely nothing to do with this popular misconception of being emergency memory or kind of slower RAM as some people believe it is. People also have this really weird idea when talking about swap that they should disable swap because disabling it will somehow magically stop memory contention from turning into disk operations. But this is obviously not true, right? Just because you can't measure it, you just believe that that's true. It's patently bullshit. Like, if we can't evict anonymous pages, which is what happens if you don't have swap, then we're just going to thrash the file cache. We're just going to throw out the file cache. And even worse, we might be forced to reclaim hotter file cache pages than we would actually want to reclaim. So we even do something less desirable than what would happen in terms of disk I/O if you had swap. So these kind of misunderstandings have really hobbled swap's reputation, and they've led to this misconception that it's not useful if you have a lot of memory or some bullshit like that. So a swap isn't just some mechanism to expand your RAM. What is it? Well, swap allows reclaim on types of memory which would otherwise be M-locked. That is, it provides this backing store for anonymous memory which otherwise would be locked into RAM. It also allows to, by its slow nature, ramp up memory contention more gradually, which is really important to catch and kill processes which are affecting the system rather than just kind of falling over and dying. Without swap, it's really hard to run with positive memory pressure. It's really hard to run hot on memory or in a memory-bound system, because we almost immediately go from, using all of the available pages and everything working hunky-dory to, oops, you requested one too many pages and now the system is completely falling over and we get completely deadlocked. This is because running really hot on memory and running out of memory becomes really binary without swap. It just happens way too fast to act on in any reasonable way. Another thing is that if you've compiled things, you've probably seen, this make-j cause +1 stuff. Well, why do we do that? Well, we do that because we want to fill up any of the remaining slack by work reappearing or work going away from increases and decreases in demand. And we want to do this with memory too. We want to always be pushing it just a little bit so that we can make the absolute maximal use of everything that we have. And this comes back to what I mentioned earlier about us as the operating system, as the Linux kernel, wanting to promote the most efficient use of memory possible. And we want to do this without impacting system latency too much, so we do need to be careful in the way we do that. Without swap, Memory contention increases by comparison are really just very, very sudden. Often systems aren't really recoverable from that state, and I'll go into an example case of that later. That is, when we go over the edge, we end up just recycling pages so fast in and out from disk and into memory that we can't make real forward progress anymore. And swap does come with some trade-offs, but in general, it does prevent a lot of these situations from occurring in the first place. And if you're generally of the opinion that swap isn't useful or it's some relic from the past, I really do recommend reading the post of this link and taking a look at what's contained there. I hope it will give you some insights into how we want to use it. One reason that people particularly don't like swap as well is because it can delay invocation of the killer. The kernel killer is essentially what's invoked when the system is ostensibly out of memory. And it's essentially a massive cannon that you fire at some process and you pray that you fired it, in the right direction. And usually you fired it kind of in the wrong place. And these are part of the two fairly major constraints of the killer. Number one is, if you invoke it, you've probably already lost. Probably everything on the system now is pretty much queued up. Due to the fact that memory hotness information and memory access information is hidden behind the CPU's memory management unit, we don't actually know as the kernel when we are out of physical memory in a readily available way. This might come as a surprise, but it is true. Linux really just has absolutely no idea when you are out of memory. It only knows when it tries really, really, really hard to go and get some more memory, to go and free some pages, but it couldn't do it for quite a while. Generally, this is because only the CPU propagates this MMU page hit information, that's this PTE young stuff, and calculating it ourselves would be way too expensive. So we have to proactively pull this information when we're trying to free pages. That's what reclaim means. So the problem here isn't knowing when our memory is full, we know that, because our goal is all the time to have our memory as full as possible, basically. It's easy to know how many pages are resident. What's not so easy is knowing how many pages we could easily free if required. And as discussed, we don't really know when we're out of memory because we need to reclaim first to know that information, which can take a really, really long time. It's a very expensive process, potentially involving all kinds of I/O. As you'd also imagine, we only want to invoke the killer when we actually are out of memory. So this means there can be a really long time after totally running out of memory that you wait before you actually get the killer invoked. So we already have to go through a lot of reclaim attempts, we might have to do a lot of disk I/O, we might have to look at the MMU hotness statistics. So relying on the killer to do something on your system in a timely fashion is really a fool's errand. It might happen to work for you right now, but there's a million other cases in which it will not work for you and in which your system will grind to a halt. So our goal in general should be to avoid having to invoke the killer at all and avoiding memory starvation in the first place. And I'll come back to how we go about doing that reliably at scale in a slide or two's time. A second problem with the killer is that it's not really configurable. We have this thing called scores. I love anything in the kernel called a score because it means that when we designed the interface, we really had no fucking clue how it was supposed to be used. In general, nobody knows how this is supposed to work. Even the people who work on memory don't know how this is supposed to work. You either set it to minus 1,000 or plus 1,000, or I think 999 is probably the limit. You set it to the maximum limits or something, or you set it in the middle, and you kind of pray that it's higher or lower or somehow somewhere different than some other application. And in general, nobody knows how this is supposed to work. It does play into the killer's heuristics about what to kill, but aside from the absolutes of minus 999 or 999 or whatever, it's really hard to reason about what that's actually going to make the killer do, and how exactly the killer is going to behave and whether it's going to have the desired effect or not. So this often means that the killer will just kill the complete wrong thing on the system. It often just kills the largest thing on the system, or kills things until it randomly kind of finds the one which was causing the problem. So obviously not a great solution to the actual problem there. So I keep on bringing up this thing called reclaim. It's probably worth going a little bit into how that works. So reclaim is just a fancy word for this process of trying to free pages. There are many different ways in which reclaim could happen. Two common ways are this kswapd reclaim or direct reclaim. Kswapd reclaim is done by a background kernel thread which tries to proactively free some memory when we are reaching some threshold. For example, if you use 95% of memory or something like that. Kswapd reclaim avoids going into this next and scary phase of reclaim, which is called direct reclaim, which is what happens if your application requests memory, but there isn't any available right now. This can result in your service having an actually measurable freeze, which obviously sucks, because what's going to happen is we're going to actually suspend the application from execution while we go and try and get some memory. So that's why we have this other proactive kswapd kernel thread, which avoids getting into this direct reclaim state in the first place. Reclaiming some pages may also be easier or harder than others. We talked a little bit earlier about this reclaimable memory stuff and what it actually means. Some pages may be reclaimable, but just not right now. For example, some cache pages may be so hot that it makes no sense to evict them right now, and the applications accessing those pages would just be driven into the ground if we tried to do so. And the same goes for anonymous pages if you don't have swap. If there's no swap free or there's no swap available, then without a backing store for that memory, it's just locked in memory and you can't do anything with it, which kind of breaks down memory management because you simply cannot reclaim a huge class of pages. Some page types may also be reclaimable right now, but it takes some effort in order to do so. For example, dirty pages, which are pages in the page cache which have been modified and are waiting to be written back to disk, need to be flushed to the disk first before we can actually proceed in freeing them, right? Otherwise we'd either lose the modifications to the file or even potentially corrupt the file system or other critical parts of the system. In practice, this variance and unpredictability in reclaim means that it's typically really hard to tell ahead of time when you're actually running out of physical memory. But if we wanted to know that, how would we go about it? If I were to ask you to tell me, how would you tell if your machine was oversubscribed on memory? What kind of metrics would you traditionally look at? Well, when I ask this question at conferences, typically the answer I get is something like, look at the free memory. But the problem with looking at free memory is that it doesn't tell you anything really, because in general we want to use all of the available memory on the system as much of the time as possible. So it's going to say it's full almost all of the time. And then usually somebody says, okay, we'll just subtract the caches and buffers from the free memory. But again, some caches and buffers might actually be needed. They might not be able to be reclaimed at this particular point in time. So you really can't just subtract them and expect that to make sense. Another metric that often some more senior engineers bring up is page scan rate. Page scan is essentially the rate at which we are going through pages trying to reclaim them, trying to free them. And if it's very large, it means we are having to scan a long way through the memory lists to try and find some pages to free which are eligible to be freed. And the problem with page scans is it's very hard to differentiate a very efficient use of the system from oversubscription on the system. So it's not really easy to tell just from these metrics whether you're tipping over the edge or whether you're in a perfectly steady state. There are other metrics, of course, we could spend all day going through them, but all of them up to this point have their caveats and limitations, and they can all trigger under normal operation and useful system state, as well as actual system instability and oversaturation. So usually all of these metrics which we come up with are just approximations of memory pressure. So what is memory pressure? Well, we've never really had a metric like memory pressure in the kernel before. We have many related metrics like the ones we've just been over, but even with all of those metrics, it's really hard to tell, what is real pressure and what is just a very efficient use of the system. For example, in memory, we might want to be able to tell, how much of the time are threads on the system being stuck doing memory work. And we have this new kernel feature called PSI, which for memory, for example, can tell you the amount of time that threads on the system were stuck doing some kind of non-ideal memory work, like faulting back in pages or doing some kind of work which, if we had more memory, we probably wouldn't need to do. So the word sum here, the line sum here, means some threads in that Cgroup were stuck doing this non-ideal memory work for, say, 0.21% of the time in the last 10 minutes. And full means the same, except for all threads in the Cgroup were stuck doing that. This could be things like, waiting for a kernel memory lock, being throttled, waiting for reclaim to happen. Even more, it could be just, waiting for disk I/O, waiting for things to be swapped, waiting for page cache faulting, and stuff like that. So pressure is essentially saying, if I had more of this resource, I probably could run 0.21% faster. So it's quite a useful metric if you're developing high availability applications or high reliability applications and stuff like that. It really gives you an overview of how your system is operating, not just at an ideal circumstance, but whether it's being oversubscribed and stuff like that. For example, For the high availability and high reliability use case, we at Facebook use this to know in advance whether we're about to use too much memory for async jobs, for background jobs on the web servers. And we do load shedding. We can say, you know, we couldn't take that much more memory ahead of time. We know when we are actually reaching memory saturation using this metric, which we don't know with any of the other metrics. And you can't measure this just by looking at resident memory, because again, you simply don't know what's reclaimable and what's not ahead of time. These PSI metrics are also what powers our preum detection at Facebook, and we do this as part of a project which we've open sourced called UMD. UMD is essentially a user space killer with a really fine-grained policy engine, and this allows you to encode policies of what to do in certain memory pressure situations. For example, we run Chef on our machines as part of configuration management, and while Chef is important, if we're running tight on memory, we can live without it for a few minutes, and the same goes for other background work which isn't customer-facing. UMD allows you to encode things like that based on these pressure metrics. For example, we might be able to measure a best effort application's pressure metrics, and if the best effort application starts to cause contention for others or cause system-wide contention, we can either kill it before or performance degradations happen, or throttle it, or do whatever we want. Using these metrics, we can prevent entirely while still preserving system stability and avoiding grinding to a halt system-wide. And the same cannot be said when the kernel killer is used, because again, it often results in a significantly degraded system for long periods of time, simply because it has to go through so many reclaim passes, whereas we can passively monitor it through system reclaim in general. Another thing which you might have seen me talking about in the old days of Cgroup 2 was limits. That's this memory.high and memory.max stuff. And the initial proposal for Cgroup 2 was to limit non-essential work in the machine, kind of a traditional approach. But this has, among a few other things, a few major problems. One fundamental problem is that it doesn't treat applications which have highly variable resource usage very well. For example, if you have an application which uses 900 megabytes at 1 second and 1.5 gigabytes at another second, if you set the value too low to the low amount, then the application might just get killed unnecessarily. But if you set it too high, you know, the application for the majority of its lifetime might just have completely free reign over the system with no real consequences. So that becomes a bit of a problem, just using limits. It doesn't really allow for any ballparking. Another critical problem is that the resource usage of some system-wide daemons can be very heavily tied to the core workload on the machine. For example, if you have a daemon locally available which does like tier lookup or service lookup, that kind of stuff, and it has a cache, how big that cache gets largely depends on what it's asked to do by the main workload. If the web server requests some kinds of tiers which are very large, maybe the cache gets very large. And this is a problem because most fleet-wide service owners for these kind of daemons don't necessarily know what the reasonable values for their service's memory should be, because it's so variable depending on what they're asked to do. So even if they can record it right now, it could change 5 minutes in the future when they're requested to do something else. Something that we can reason about, though, is how much memory we actually want to reserve for the primary workload, like the web server or whatever. So it's much more easily configurable to make some kind of guarantees about what we will give the workload, rather than act punitively against other non-essential services when maybe we really didn't need to. Generally, large service owners like web tier owners do know roughly how much their service does require, because they know what their user base looks like, they know what their requests look like, and that's something which is a lot more uniform across the fleet. So for this reason, we've largely shifted to using and improving our protection tunables, that's this memory.min and memory.low stuff, which define hard and best effort protection respectively. And when you're below your protection threshold, what happens is that we don't reclaim memory at all from you. In the case of memory.min, we never breach, we will never reclaim from you as long as you're below your limit, and for memory.low, we would only reclaim from you below your limit if we are under system-wide memory contention anyway. This allows significantly more work conservation, allows a lot more work to happen on the machine without punishing people unnecessarily. Daemons can use as much memory as they like, as long as they don't affect overall system stability, and that's one thing which has been very helpful in developing this overall strategy for resource control. So this is all very well and good. I've gone through a whole lot of primitives, but how do we actually intend to use them? Well, this is where FBTax2 comes in. FBTax2 is our overall project for resource control at Facebook. Cgroup 2 is certainly one of the primary things which we need to achieve that. However, as we've gone over in this talk, We also need a lot of other supporting elements to work and be in place to make it actually compose to a functional and coherent system. So one concern, of course, is stopping background services that the main workload isn't dependent on from affecting the workload. For example, as we mentioned, metric aggregation or configuration management going crazy and like stealing memory from the web server, or running the machine out of memory entirely. We also want to have reasonable behavior if we start to exceed the capabilities of the hardware if we try to use too much memory. Again, to scale to our future capacity needs, we do need to have this high resource density. We need to be having high memory pressure and making the best use of positive pressure. So, of course, this does come with the risk of going over the edge, pushing it a little bit too far, right? So we need to have graceful behavior when we do inevitably push it a little bit too far. It's also really important that our efforts are kind of lightweight. It's no good if we can now load machines 10% more if we also take 10% of load of the machine to do it, if you get my point. It's also no good if we, produce this very technically incredible solution, but it's such a burden on site operation or maintenance or service operation that nobody actually wants to use it in practice. So we have to make it usable, and that's one thing we've been very conscious of when designing Cgroup 2. So FBTax2 in general comprises a really wide range of solutions to compose to a usable system. We do need to tune the base OS and be opinionated to make sure that it's capable of isolating resources. Otherwise, on non-compliant systems, we might actually end up breaking down and making things worse than doing nothing at all, as we mentioned earlier. We also have the aforementioned early killer, OOMD, running on FBTax2 machines. On those machines, it monitors for threats to the workload and misbehaving workloads on shared machines. It prevents these very obviously misbehaving applications from posing a threat to overall system health based on the policies which you've assigned. As for how this actually looks at the base OS layer, we use Btrfs as the root file system. This is needed because, as mentioned, we have some fairly insurmountable priority inversions we found. One of those was in ext4, in the way in which it does journaling, where you have to flush out all of the entries in the journal at once. And one of the problems is then you cannot limit I/O for any application because all applications become contingent on it completing. So if you have some low priority application in the journal and some high priority application in the journal, the high priority one becomes contingent on the low priority entry's journal entry being completely flushed to disk. And because we're throttling, that's not going to happen, so bad things occur and the whole system slows down. So fixing these kind of things wasn't really possible on ext4, but it has been possible on Btrfs. We do have a lot of the Btrfs core maintainers at Facebook, obviously not a coincidence of why we've been able to do a lot of these things, but in general Btrfs's design is far away from the memes of like 10 years ago where everyone was complaining Btrfs ate my data. Nowadays we use it on tons and tons of systems. I can't say an exact number, but a lot of systems, like a lot of digits of systems, and it works just fine. In fact, it detects a lot of hardware issues which are not detectable due to the way it does checksumming and stuff like that, sorry, which are not detectable by things like ext4. So that's one reason people often complain, Btrfs ate my data, and the reason is because no, it actually detects these issues which other file systems are not detecting. I also mentioned earlier about the importance of swap. Usually we might disable swapping on the main workload. It kind of depends a little bit on what it does. It may or may not be reasonable to have it enabled for a particular workload. We do need swap though system-wide to make sure that we're efficiently able to reclaim all types of memory and not just a limited subset. We're also opinionated about some kernel tunables. One of them is WBT, or write-back throttling. If you used desktop Linux in the past, and I assume you do since you're at ArchConf and most people are probably using it on the desktop, you may have encountered the situation in the bad old days where you plugged in a USB drive, you tried to copy some files to or from the USB drive, and the whole system would just freeze completely. The reason for that is because a write-back is generally not stoppable. Like when you've issued a write-back, everything, the forward progress of the system becomes contingent on write-backs completing. And your whole system is kind of stalling because like this I/O is the most critical thing it's doing at that point in time. It's a little bit complex to explain, but the general principle is you cannot slow it down, you cannot stop it. So this is what write-back throttling is designed to address. Write-back has this special property, as we mentioned, that due to the way it's implemented, we cannot slow it down or stop it. So write-back throttling is a way of us avoiding issuing the write-back in the first place and slowing it down if we are exceeding some threshold or if we know we're causing the system pain. Cgroups are also the bread and butter of resource control, so as such it does make some sense to go into our choices in terms of configuration there. To get sensible resource control, it's very important to have these clear definitions of roles from the top level. For example, we have system.slice, which is a slice for work which is not time sensitive, for best effort, nice to have services which can be killed or throttled in an emergency, like chef or some metric aggregation, that kind of stuff. We also have host-critical.slice, which are for daemons which are required by the system to run. These are typically things that we need for debugging, like SSH, logs, also some systemd daemons, some dbus daemons, that kind of stuff. And we want all of these to work even if the system is generally not having a very good time. We also have workload.slice, which is for the key workloads which are running on the machine, for example, HHVM on a web server or MySQL on a database server. And having these really clear distinctions allows us to know exactly how we're going to propagate resources from the top down based on service role, which makes life a lot easier. This is actually how this used to look, which is punitively limiting the best effort work. As we mentioned earlier, this is fairly brittle. System.slice memory, for example, might legitimately spike, and that might be okay in some circumstances. And we might end up slowing down or killing things when we really actually didn't need to. The workload didn't need that. It's also really absolute. It doesn't really allow for any ballparking. If you set a limit, a memory limit, we're going to enforce it absolutely. We're going to take some punitive action on the application if you exceed it. So it's not really great for applications which have highly variable resource usage. So we need something that can help with that. And that's why we've changed from using that to this memory.high, from this memory.high and memory.max stuff to using protection. That's this memory.low and memory.min stuff. And again, these are kind of a guarantee that we will reserve some memory for that process. We don't prohibit any other application from using it, but we aggressively take it away from them if the workload does end up needing it. And this allows ballparking significantly more easily because you can set these kind of thresholds without affecting overall system throughput and system stability. You'll also notice the addition of io.latency. This is a new kernel feature which we've been working on at Facebook, but it's available in modern kernels everywhere. Use Arch Linux, so you probably have it. And we didn't really have time to deep dive into how this works, but essentially it works by providing disk I/O latency threshold. That is, you guarantee some amount of I/O completion responsiveness to the main workload, and some other level to the best effort, and some other to the host critical services, and it keeps on degrading until it reaches each of those thresholds. I/O control is really important when limiting memory, as we discussed, and if an application is misbehaving, it can just really cause huge I/O storms if you're limiting its memory. So this is one reason why we really need this. So having these completion latency guarantees, the write-back throttling, and UMD really permits stopping these bad applications from affecting system stability overall, and this happens before they affect system throughput and stability at large. I also mentioned I don't want to just talk about abstract theory, I also want to talk about production success stories. Well, in this case, we intentionally cause a fast memory leak in systems.slice on Facebook web servers, the best effort slice. Don't worry about all of the colors and lines and little bars yet, we'll go over those. Essentially, the purple line is without fbtax2 and the green line is with it. With a normal operating system setup, the crux is basically that it takes in the order of minutes to recover from a 10 megabyte a second leak. And this is basically nothing. That's pretty tame compared to a lot of real life situations. This is another example of why when people think that the killer will come to their rescue, it simply won't. This is all works based on reclaim. So again, if it can make progress, if it's making progress system-wide doing reclaim, the system will not invoke the killer, even though your application might be being completely driven into the ground. And only after an incredibly long time, sometimes in the order of a double-digit number of minutes, does the system realize it's not actually making any forward progress, long after, a fleet-wide event could easily have taken out your entire service. Contrast that with the fbtax2 case, where we quickly isolate and stop the leak before it actually affects machine or workload stability. Now we can have significantly better control over resources and can not only increase fleet-wide stability, but also fleet-wide efficiency, which is quite important considering the crunch which I mentioned earlier. In fact, we can repeatedly relaunch the same memory leaking application over and over and over, and it has no effect on the workload whatsoever, due to the fact that UMD is killing it and the fact that we are throttling it beforehand. This is made possible by all of the primitives which I've been talking about in this talk, working in tandem. No one of them could do this alone. And this is what I was talking about when I said we had to build a complete and compliant operating system in order to perform resource control reliably, and none of these can do it by themselves. On tiers which run some of the web background jobs at Facebook, some of the primitives mentioned were even part of permitting them to run on smaller and more efficient machines. Previously they couldn't move because there was so much uncertainty about the variable memory use of their workloads. But now they can actually use some of these primitives mentioned to reliably measure, can they take on more load or should they do load shedding, which was a huge part of allowing them to migrate to smaller and more efficient machines, which is another huge win from these efforts. One thing I'm pretty excited about is that the new technologies which I've presented in this talk are allowing us to do things which we've simply never really been able to do before as engineers or in Linux. So I really hope that I've been able to give you some idea about how these tools and technologies might be able to help you in your specific line of work. And I'm really looking forward to seeing what new novel things people in this conference might be able to build using what's presented here in the coming years. I've been Chris Down, and this has been Linux Memory Management at Scale. Thank you very much, and have a great day.